Hello class. The topic for today is cross products. And to focus on a specific aspect of cross products, I want to teach you three ways to evaluate a cross product. Now each of these ways of evaluating the cross product has its strengths and weaknesses, and I'll also explain some of those as I go along. So the primary method of evaluating cross products for basic physics applications is the traditional one of so I'm going to take two vectors A and B and indicate the cross product C as A cross B. So if I'm given vectors A and vectors B, I wish to make sense of A cross B. Well, in physics applications, the way we think about A cross B is very intuitive. You have a vector A here and some other vector B there, and A cross B is a vector got by moving your right hand fingers from A to B and you're curling it, as it were. And so when you curl it, the A cross B vector is a vector that's perpendicular to both A and to B. So if I were to write this angle here would be 90 degrees, and that angle would also be 90 degrees. So the cross product has the property that it's perpendicular to both the vectors that make up its constituents. So C is perpendicular to both A and B. Another way to think about it is the following. C is in the plane that is perpendicular to A and B. So A and B together form a plane, and C is perpendicular to that plane. So that's a geometric intuitive way of looking at the cross product. Now let's actually try to evaluate a cross product using this philosophy. So I'm going to take a specific example here of A equals 5i hat minus 2j hat plus k hat. And this is just, I'm randomly picking up numbers here. I have no reason to prefer this over anything else. Let me just take 6i hat, and just to make things easy, I'll take one of the components to be 0 j hat, and I'll take some negative 3k hat here. So these are two random vectors, and in a physics application, this could be the r vector, that could be the f vector. So you will get torque, or if it's angular momentum we're talking about, angular momentum would be c, and that will be the r vector, and that will be the momentum vector p. Or it could be something like in UP2, you could be looking at the magnetic force F, and then this it'll be charge times this will be velocity, and that will be the magnetic field, incidentally called B. So this could be a number of cross products, and cross products are very ubiquitous in physics. Now, one way of evaluating the cross product is to use the basic definition of what a cross product is. The magnitude of the cross product, which I'll write simply as C, is going to be the magnitude of A cross B, and that is equal to the magnitude of A times the magnitude of B times sine of the angle between the two. This is the definition of cross product I introduced in a previous video to do with Newton's second law of rotation. You can actually use this definition to evaluate not the direction but the magnitude. The direction is always going to be given by your thumb, and that is all you can really say. You can say the direction is that, and you can't do anything more than that. But the magnitude you can evaluate. So I'm going to write this as AB. Now the sine of the angle between the two is not easy to calculate, but you can certainly calculate the cosine of the angle using the dot product. So I'll write this as 1 minus cosine squared theta from the relationship between sine theta and cosine theta. And what I'm going to do now is to evaluate cosine theta. Now cosine theta, if you recall the dot product of two vectors, it's a dot b equals the magnitude of a times the magnitude of b times the cosine of the angle between a and b. So I can find cosine theta directly. So I'll do that here. Cosine theta equals a dot b divided by the magnitude of a times the magnitude of b. So that's interesting. So I'm going to square that in here. Let's see what I get. I get ab times the square root of 1 minus a dot b squared over a squared b squared. And when I take the common denominator here, I'm going to end up with ab times the square root of a squared b squared minus a dot b squared divided by, that's going to be the square root of a squared b squared, or just ab. So you'll notice that this ab cancels out. And so a really nice way of evaluating the cross product of something is to find the magnitude of a, square it, the magnitude of b, square it, and subtract from that product the dot product of a and b squared. So these steps can be carried out pretty efficiently. So I'm going to work out the magnitude of a on the right side. The magnitude of a is by the Pythagorean theorem in 3 dimensions. It's going to be 5 squared plus negative 2 squared plus 1 squared. So that's 25 plus 4 plus 1. That's 29 plus 1, 30. So that's root 30. And the magnitude of b, likewise, is going to be the square root of 6 squared plus 0 squared plus negative 3 squared. So that's 36 plus 9, or 45. Okay, it's what it is. Now a dot b, remember how a dot b is got. It's got by multiplying the x component of a with the x component of b plus the y component of a times the y component of b plus the z component of a times the z component of b. So that's the how we do the cross product, dot product, excuse me. So that's going to be 5 times 6 plus negative 2 times 0 plus 1 times negative 3, and that's 30 plus 0 minus 3, or 27. And now we just have to stuff all these numbers in. Let's do that. That's going to be the square root of, now when I square the square root of 30, I just get 30 times 45 minus, that's 27 squared. So I use my trusty calculator here. I'll do it off to the side. I don't want to keep it on the sheet there. So this gives me the square root of 1350 minus 29 squared, 27, excuse me, 27 squared is 729. So that's square root of 621. And I'll just leave it like that. It's close to 25, but I'll just leave it like that. So that's the magnitude of the cross product. The direction, as I told you, cannot be found because it's the direction of your thumb, whatever that direction happens to be. But the magnitude can be found using the most primitive definition of the cross product. So now let's go to the second way of looking at cross products. This has to do with the distributive property of the cross over addition So I'm going to write the cross product using that distributive property. Let me show you how that's done. C equals A cross B. For A, I'm going to put 5i hat minus 2j hat plus k hat, and for B, 6i hat. I will not write 0j hat. It's going to eat up space, so I'll just write it as that. And now what we do is we multiply this as though we were multiplying numbers, except we'll respect the appearance of the cross product between these unit vectors. So 5 times 6, it's 30 I hat cross I hat, and then I'll do each one of these things with this term, and then I'll do each one of these things with that term. So then I have negative 12 j cross I, and then plus 6 k cross I, and then now this one, negative 15 I cross k, positive 6 j cross k, negative 3 k cross k. Now, if we are able to evaluate all these unit vector cross products, we'll be done. We'll have the complete expression for the magnitude, of the vector form of the cross product, and then we can find the magnitude if necessary. So here's the trick here. You put I hat, j hat, and k hat in the 12 o'clock, 4 o'clock, and 8 o'clock positions of a clock, and draw arrows. If the clock is moving, if the hands are moving in the direction of the clock, it's positive. If it's going opposite the direction of the clock, it's negative. So based on that, we're going to write our rules. I cross j, well, it's moving in the direction of the clock, so it's going to be k. J cross k, I, and k cross I, j. If you're going against the clock, you're going to get the negative value. So for example, j cross I, well, that's going against the clock, so it's minus k. The other one would be k cross j, and k cross j against the clock, minus I, and the last one would be I cross k against the clock, minus j. And the last set of rules is that if you don't move, if you're not moving, if it's I cross I and j cross j and k cross k, it's all 0. And when I write 0 vector, I really mean 0 in the I hat direction, 0 in the j hat direction, and 0 in the k hat direction. That's what the 0 vector stands for. So basically, if you're stagnating, then you get 0 result. Let's use this commutativity and anti-commutative arithmetic to actually solve this problem. Now, I cross I is 0, so I won't write that. J cross I is minus k. Well, that minus k and the minus sign here cancel out, so I get 12 k hat. K cross I is j. I cross k is minus j, and that minus cancels with the minus here, so that's 15j. And lastly, this is 0 because it's k cross k, so I won't write that. I'll just put 0 through those things. J cross k is I hat. So I'm going to just get the following answer. it is 6I hat plus 21J hat plus 12K hat. So that's the complete answer. It's a vector answer. Now, just to make sure we were consistent with that, I'll find the magnitude. The magnitude is going to be given by the 3D Pythagorean theorem here, and that's going to be 6 squared plus 21 squared plus 12 squared. So let me quickly work that out. That's 36. 21 times 21 is 441, and that's 144. I'm going to quickly add these three numbers off the screen. And indeed I get 621. So this was exactly consistent with that. Now the last and the final method of evaluating the cross products. I'll keep this method for a separate video because I'm already running over the 15-minute limit, which I like to keep these videos just 15 minutes long, or approximately 15 minutes. So for the last one, I'll actually make part 2 of the same video because it'll take a while to explain the last method. So look for part 2.